All right, I'm gonna continue here. Number 19. Limit x goes to 1. X to the a minus ax plus a minus 1 over x minus 1 squared. All right. So a here is a constant. X is our variable. Let's let x go to 1. So 1 raised to any power is 1. So that's a 1. Minus a times 1 is just a, plus a minus 1. So that's the top, that's 0. And then 1 minus 1 is 0, square root of 0. So we have 0 of 0. Bring in L'Hopital. Derivative of the top. All right, well, this is x to a power, so that's like, x to the 5th. We use power rule. 5 comes out, right? So here a comes out. X to the a minus 1. I don't know what a is, so that's the way I have to write it. Minus derivative of a times x is just minus a. That's a constant, so derivative of both of those are 0. This should be minus a down here, like that. And then derivative of this is chain rule. We have something squared, so 2 pops out, then x minus 1 to the first power times the derivative of what's inside, which is just a 1. All right, so that's it. Let x go to 1. 1 raised to any power is 1. So that's a times 1, that's a. A minus a is 0. X is 1, so 1 minus 1 is 0. 2 times 0 is 0. So we still have 0 over 0. So that equals, by L'Hopital's rule again, all right, so I have to do the derivative of this. The a is a constant, it's going to come for the ride. This is x to a power, the power comes out front. So I already had an a there. Now an a minus 1 drops out. X to the, well, I have to subtract 1 from this again, so that's a minus 2. And then derivative of a constant here is 0, so just this, over the derivative of this here. 2 is a constant, comes for the ride. Derivative of x minus 1 is just 1. And now let's let x go to 1 again. 1 to any power is 1. So you're going to get a times a minus 1 all over 2. Interesting answer. It's just a busy, busy day. Done, done, done. Right. 19 is done. (21) Limit x goes to 0 of cosine x minus 1 plus 1/2 x squared over x to the 4th. If x goes to 0, cosine of 0 is 1. 1 minus 1 is 0. That goes to 0. That's all 0. So we get zeros on the top. On the bottom, of course, 0 to the 4th power is still 0. So I'm going to use L'Hopital. L'Hopital. Derivative of cosine x, negative sine x. Derivative of negative 1 is 0. Derivative of this, 2 pops out. Half of 2 is 1, so this just becomes plus x over 4x cubed. That's a 3. Try it again. X goes to 0. Sine of 0 is 0. That's a 0. That's a 0. So I get 0 on top. And of course 0 on the bottom again. L'Hopital again. Limit x goes to 0. Derivative of sine x is cosine x, but there was a negative out front. Derivative of x is 1. Derivative of 4x cubed is 12x squared. Let x go to 0 again. Cosine of 0 is 1, but it's negative. So negative 1 plus 1, that's 0 on top, 0 on the bottom again. All right, L'Hopital again. Derivative, there's a negative here, I'm going to cover it up. Derivative of cosine x is negative sine x, but then I make it negative again, so that's positive sine x. Derivative of 1 is 0, over derivative of the bottom is 24x. Let x go to 0, sine of 0 is 0, over 0 again. L'Hopital again. I think this is it. I think we're finally going to get it here. Derivative of sine x is cosine x. Derivative of 24x is 24. Let x go to 0. Cosine of 0 is 1 over 24. 1/24. That's cool. I can't be there. Oops. Twenty-three. Limit x goes to 0. Cotangent 2x times sine of 6x. All right, this is getting ridiculous. The emails just keep pouring in. All right, so cotangent of 2x. You have to kind of know what happens. If x is 0, this is 0. Cotangent of 0, you can go and take a look at the graph, or you can remember that cotangent of 2x is the same as this. So what we have here is, by the way, this is sine of 0, which is 0. So this is going to 0. And cotangent, well, why don't we just look at the graph of cotangent? I think that'd probably be the easiest thing. And I believe your graphs are on page, where is it? Reference page 2. So cotangent, if we look at cotangent, I could do this, it'll be fixed over 0, all that, but if I just look at the graph of cotangent, here's pi. We have asymptote here and here, and it goes like this. Something like that. So as you can see, am I approaching from a certain side here? Well, if I approach, let me do it this way. It's not telling me which side to approach from. So if I come in on one side, cotangent of 0, I'm infinite. If I come in the other side, I'm negative infinite. Either way, this is plus or minus infinity times 0. And this is still an indeterminate form, so I cannot figure out what that is. I have to do something. But it does not look like L'Hopital's rule. It does not look like 0 over 0 or infinity over infinity. So this is where we use a little trick. What we do is we rewrite the problem, and we take one of these guys and we drop it to the bottom. So I'm going to leave the sine 6x here because it's nice. Over, I'm going to write the cotangent 2x on the bottom as 1 over cotangent 2x. Because in reality, that would just flip back up and it would just be that. However, by doing it that way, I can now rewrite 1 over cotangent 2x. I can rewrite that as tangent of 2x. And now let me see what happens when x goes to 0. Sine of 0 is 0. tangent of 0, remember a graph of tangent looks like this. Tangent of 0 is 0 also. So now this looks like 0 over 0. So I've just rewritten the form of infinity times 0 as a different form of 0 over 0. And now I can use L'Hopital. So when I use L'Hopital here, I'm say this is equal to the limit as x goes to 0. I'm going to take derivative of the top, which is 6 cosine 6x, and derivative of the bottom, which is 2 secant squared 2x. I hope you follow me there. Chain rule on both of those, and I just move the constants. The constants that pop out from here, I just moved them out front. Now let's let x go to 0. 6 times 0 is 0. Cosine of 0 is 1. So the top is headed towards 6 times 1, which is 6. All right, secant of 0 is the same as 1 over cosine of 0, which is, cosine of 0 is 1, so that's 1 over 1. This right here is 1, and then you square it, still 1, and then times 2, so you get 2. So the answer here is 3. $25. Limit x goes to infinity. X cubed times e to the negative x squared. It's going to be a little tricky. All right, so let's see what happens when you let x go to infinity. You get infinity cubed, that's infinity, times, right, times e to the infinity squared is infinity, but negative infinity. So that's a little tricky. E to the negative infinity. What that really means is look at your e function and don't head out to positive infinity and tell me it's going up forever. You need to head to negative infinity, so you need to head this way. You can see that the function approaches 0 asymptotically. So it's getting closer and closer to 0. So this is headed towards 0. This is headed towards 0. This is headed towards infinity. So we have infinity times 0 again. We are not allowed to use L'Hopital's rule for that. But when we see this, we take one of them and we drop it down. So I think the most natural one to drop down would be this one, because it's a negative exponent. I can already just rewrite it on the bottom as a positive exponent, right? Now I have a fraction. X goes to infinity. The top goes to infinity. Infinity. Over now e to the positive infinity. That's where e goes up. That also goes to infinity. So I have infinity over infinity. I can use L'Hopital's rule. So this will be equal to, by L'Hopital's rule, the limit as x goes to infinity of the derivative of the top, 3x squared, over the derivative of the bottom. So be careful here. It's derivative of e to anything is itself, times the derivative of what was up here, up there. The derivative of x squared is 2x. One of these x's cancels. So we have limit, x goes to infinity. I still have 3x on top, and on the bottom I have 2e to the x squared. And now, look at it, x goes to infinity, 3 times infinity, that goes to infinity, over e to the infinity squared. This is all infinite times 2, still infinity over infinity. So I go with L'Hopital again. Limit x goes to infinity. Derivative of the top is just 3. Over derivative of the bottom, the 2 comes for the ride. E to the x squared. Derivative of e to the x squared is itself. There it is. Times derivative of what was up here, 2x. And now let me try and let x go to infinity again. The top just stays at 3. And the bottom is like e to the infinity, which is infinite, times 2 times infinity. That's basically infinity times infinity. 2 times infinity, that's infinite. So you get infinity here. So you have a fixed number over infinity. That means the top's staying the same, the bottom's getting huge, the fraction gets small. This goes to 0. There you go. 26, limit x goes to 0 from the right. Sine x times natural log x. All right, plug in 0. Sine of 0, 0. Natural log of 0, well, we're approaching 0 from the right. Here's your natural log function. As we come in from the right to 0, it goes to negative infinity. So this gives me the form of 0, that's this, times negative infinity. That is not good, so I'm going to take one of those and drop it down. Now, which one do I drop? Well, I'm going to choose to drop the sine. Now, the reason why I'm doing that is because if I drop the sine, it's 1 over sine. And I know that's cosecant. And if I drop the natural log, then it's 1 over natural log, and that might be a little harder to take derivative of. So, just rewriting now. All right. I can double check it. As x goes to 0, natural log of 0, as we come in from the right, we know that that's headed towards negative infinity, over cosecant of 0. So you could look up your graph of cosecant if you want, or you could just graph it real quick. Remember, cosecant is the reciprocal of sine. So here's the sine curve. That's sine. And then to graph cosecant, what we did was at every x-intercept, we draw an asymptote. And then from the peak of the sine curve, we draw these little like U's. That's what cosecant looks like. That's from pre-cal. And I want to know what happens at cosecant of 0 as we approach 0 from the right. So here's cosecant, here's 0. Approach it from the right, we go to positive infinity. So we have infinity over infinity, basically. And we can now do L'Hopital. L'Hopital. Derivative of natural log of x, 1 over x. Derivative of cosecant x is negative cosecant x cotangent x. Eee. That does not look like that got any better. That looks like it got uglier. All right, I'm going to have major problems. If I try and let x go to 0 right here, I have fixed over 0. That's going to become infinite. And then down here, I'm going to have some issues too. Whoa. Okay, so let me try something before I go on. Let me rewrite this. I have limit x goes to 0 from the right. I have 1 over x over negative, okay, cosecant is 1 over sine x times cotangent, which is cosine x over sine x. All I'm doing is rewriting. Not doing any L'Hopital right now. 1 over x over negative cosine x over sine squared x. What I did is I created a fraction over a fraction so I could flip it and do reciprocal, all that stuff. Trying to get an idea of what this thing does. See if I can do L'Hopital again. Okay, so when I flip this up, the sine squared x goes on top, the negative cosine x goes on the bottom. And so I have sine squared x over negative, let me put the negative up here. It doesn't matter if the negative's on top or bottom. X cosine x on the bottom. What happens as x goes to 0? If x goes to 0, we get sine of 0, which is 0, squared 0, negative 0, so it's 0 on top. And then 0 times cosine of 0 is 1, so this is 0 over 0. I'm really hesitant to do L'Hopital again, because I could probably get this without L'Hopital. But I'm going to do it, because the section is about L'Hopital. I have to take derivative of the top, and that's chain rule, because it's something squared. So the negative stays, the 2 comes out, sine x, so that drops the 2 out, times derivative of the inside, which is derivative of the sine, which is cosine, over, now we have down here a product rule. Derivative of the first one is 1 times cosine x, plus derivative of the second one, which is negative sine x, so I'm going to put minus sine x, that, times the first one, which is x. Ugh, this does not look like it's getting any better. Let's let x go to 0. Sine of 0 is 0, cosine of 0 is 1. That top is 0. Over, cosine of 0 is 1. Minus sine of 0, 0 times 0. That's all just minus 0. This is 0 over 1. The answer is 0. That's awesome. It worked. What number was this? 26? All right, let's look at 27. Limit x goes to 1 from the right. Natural log x times tangent of pi x over 2. I'm going to write that as pi over 2x. That's the same thing. All right, as x goes to 1, natural log of 1 is 0. So that's headed towards 0 times, all right, let's let x be 1, pi over 2. Tangent of pi over 2. Here's your tangent function. Here's pi over 2. We have that asymptote. It's headed towards infinity there, so that's infinite. Okay, so I've got to pick one of these and drop it. Ugh. See, here's the reason I'm hesitating to drop the natural log down. If I drop it down, it's 1 over natural log x. And if I have to take derivative of this, that's going to require either quotient rule or me bringing this whole thing up as natural log x, the entire thing to the -1, and then doing chain rule on it. I'm hesitant to do that. I would prefer to drop the tangent down. If I drop the tangent down, it would be 1 over tangent. That's cotangent. That might be a little easier to work with. So that's what I'm going to do. I'm going to leave the natural log upstairs. Not doing any L'Hopital. I'm just rewriting. Natural log x over 1 over tangent pi over 2x, which is the same as the limit as x approaches 1 from the right of natural log x over cotangent, not cosine, I wish, cotangent of pi over 2x. All right, so I already know what happens as x goes to 1. Natural log of 1 is 0, so the top is headed towards 0. And then if x is 1, cotangent of pi over 2 times 1, that's cotangent of pi over 2. Remember, if we go to the graph of cotangent, here's pi over 2, and it went like this and like that. So this bottom part, as you can see at pi over 2, is 0. So we have 0 of 0. That's good news. We can try L'Hopital now. So that will be equal to, by L'Hopital's rule, limit as x approaches 1 from the right of the derivative of natural log of x, which is 1 over x, over the derivative of cotangent of something. The derivative of cotangent of something is negative cosecant squared of that something times the derivative of what's inside, and that's a constant in front of x, so we're just going to get the constant, pi over 2. Man, I'm really hoping that that helps. Let's let x go to 1. 1 over 1, that's 1 on top. Okay, I'm good with that. I hope this is not 0 though. All right, so if I plug in 1 here, I get pi over 2. Let's look at cosecant of pi over 2. Cosecant of pi over 2 is the same as 1 over sine of pi over 2. And remember, pi over 2 is up here. Sine of pi over 2 is the y-coordinate. That's 1. Yes. So this is cosecant, right? This is 1 over 1. Cosecant of pi over 2 is 1 over 1. So this right here is just 1, and then I square it, that's 1, and then put a negative in front, that's -1, and then put pi over 2. So I get negative pi over 2 here. And then 1 over a fraction means you can flip it. So you should get negative 2 over pi. Bam. Number 27. Man, I'm out of time. 1, 2, 3, 4. Dang it. All right, this is a good place to stop. I still need to do a few problems. Oh well. Adios.